Hello AP Chemistry and welcome to 14.4 covering integrated rate laws. So, for those of you that are in, I guess, BC calculus or even AB calculus, I don't know. Anyway, the term should be familiar, right? We have derivatives, right? And then we can integrate them, right? And those are like opposites of each other. In chemistry, right, you're not being asked to figure out how to do an integral, right? You just need to know that these are called the integrated rate laws, because what we did was we took the delta concentration over delta T, right, and then we integrated that, right? The point being, right, that this gives us our, and I forgot to include these, 0, 0. Okay, so anyway, what happens is we take those rate laws and we integrate them, right? So this is a first order rate law that has been integrated, right? A first order rate law which says that rate is equal to k times a raised to the first power, right? This is what happens when we take a second order rate law which says rate is equal to k times a to the second power and integrate it, right? And this is what happens when we take rate equals k times a to the 0 power and integrate it, okay? Now, the important thing here is that all of these rate laws written this way, which is why this is the preferred way to memorize them, right? Because there are other ways we can write them. But this models the equation for, ding, 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 a straight line, right? Meaning that we have our y's, we have our m, we have our x, and we have our b, right? Now, which means that if we take a plot of y versus x, right? Which means ln of a versus time, right? 1 over a versus time, or a versus time, right? We can use the slope to figure out our rate constant, right? So slope would be negative k, positive k, negative k, okay? Yeah. And then we could also figure out our intercept if we wanted to, okay? So what that means is we can actually plot these to get information out of our data, okay? A couple of things to take note of. These equations are also useful as written in that we can use them to find concentrations at different times, right? So A naught or A0 is always going to be the initial concentration, right? So the concentration when we start. AT is the concentration at any given point in time, right? So if I know that A happened to be, I don't know, 500, and I want to know what happens to the concentration after 30 seconds, right? I could plug that in here, right, and solve for my concentration at time 30 seconds, okay? Likewise, later on, we'll talk about how we can use these to solve for half-life, another term that should be familiar from math, right? Which is why this chapter I feel like is a relatively easy chapter, because a lot of this stuff is, they're not unfamiliar concepts, okay? All right, so let's talk about what this means, okay? So if our data fits a first-order process, right, that means if I plot ln of a versus t, I'm going to get a straight line, right? Because these are straight line. Y equals mxb plus b is the equation for a straight line, okay? Or if I were to plot 1 over a versus t for a second order process, I'll get a straight line. If I plot a versus t for a 0 order process, I'll get a straight line, okay? So how does that play out? So if we look here, we have some pressure, right? Which again relates to concentration if we're talking about gases, right? So we have concentration versus time. Here we have ln of concentration versus time, okay? So if we take a look, right, this is not a straight line. I assume you see that, right? And this is. And you'll see that this is the same data that's just been plotted in a different way, right? So we take the same information about the concentration of CH3NC, right? And we plot it in two different ways. And if it fits this one, right? If this is a straight line, the ln of concentration versus time, we know that it's a first order process, okay? We know that it's not 0 order because it doesn't fit the plot for a 0 order process. Okay, let's look at another pair of graphs. All right, so here we have the rate of NO2, right? So here we have the ln of NO2 versus time, 1 over NO2 versus time. Okay, again, same data, just plotted based on natural log or 1 over versus time. And we'll see that this one gives me a straight line, right? And so we'll think back to our equations. Which of them is 1 over concentration versus time? And that would be second order, right? Since this one gives us a straight line, we know that it's a second order process with respect to NO2. Okay? All right. Last up. All right, next up. Here we have a reaction, right, that we've graphed, and here we have concentration versus time. So since we know for this process, right, that concentration versus time, if we look here, gives us a straight line, right, we know that this one is a zero order process, right? Now, don't confuse this with what we talked about at the beginning of the chapter, right? Because a concentration versus time graph, so since this is a curved line, we know that this different process is first order. But don't forget that there is information we can extrapolate from this even, right? We can see, right, for example, we can talk about instantaneous rates by taking the slope of the tangent, okay? That's what we talked about at the beginning of the chapter. Now, if we look, the rate here, the instantaneous rate changes with time for a first order process, which is different than a zero order process, because for a zero order process, we note that it's a straight line, right? There is no change in the slope of the tangent because it's a straight line. There is no tangent, okay? Which means that the rate of a zero order reaction doesn't change over time, right? As long as there is some of A in the reaction mixture, the rate does not change, right? Meaning that it has no effect on the rate, which is different than a first order process. Okay, last up. Next, no, still not last. All right, so the following data were obtained for the gas phase decomposition nitrogen dioxide at 300 degrees Celsius. So anytime you're presented with time versus concentration, right, time versus concentration, we should be thinking to ourselves graph, okay, which is different than before, right, when we were asked to talk about rate laws, right, and talking about rate orders. That's when we had trials and concentrations and rates. Okay, here note there is no rates, it's just time versus concentration. When we have time and concentration, we should always be thinking about graphing our data, right? And what we would do is we would plot, right? We would plot NO2 versus time. Okay, we would also plot ln of NO2 versus time. We could then plot 1 over NO2 versus time. Okay, so we would make 3 separate plots of each of these and see which gives us a straight line. And whichever plot gives us a straight line, that's what determines the order, right? So this is for a zero order. Okay, this would be for a first order, and this would be for a second order. So again, whichever of these plots gives us a straight line graph, that's what order it is. Yes, does that make sense? Okay, and that's the only way we could figure that out given this information, okay? Because this is not like those previous practice problems where we were given different kind of information. Okay, now, finally, half-life. So again, a familiar that should be concept from math class, right? Where it's the amount of time it takes to reach half of whatever your original value was, okay? Your book gives you the equation for the first order half-life, second order half-life. Do be mindful, nuclear decay, really important. Nuclear decay happens according to a first order process. Keep that in the back of your mind. Second order processes decay at this rate. Zero order, your book doesn't tell you that, but obviously you can figure it out, right? If you know that the integrated rate law for a half-life process looks like this, again, what's the definition of a half-life? Right, the amount of time it takes to reach half of whatever your original sample was, right? So if this is my original amount, what would I plug in here? Right, 1/2 of A0 equals negative k times t plus A naught, right? And then you could solve for t, and that would give us our half-life equation for a zero order process, okay? Now, things to keep in mind. What makes a first order unique relative to every other kind, and therefore easy to spot on a graph, is that the half-life is independent of concentration. First order process, half-life is independent of concentration, meaning that if we look here, right, whatever the first half-life is, the same second half-life is the same, third half-life is the same, so forth and so on, right? So if we look here at this graph of concentration versus time, right, we will see that it goes from 150 to 75 in approximately 13,000 seconds, right? We'll see that it goes from 75 to 37.5 in approximately another 1,300 some seconds, right? Which means it has a constant half-life, which means that tells you that it's a first order process without you having to do a ln of time versus graph, ln of concentration versus time graph, yes? Okay, keep that in mind also, because that's sort of a workaround, right? If we were given just this and we had to determine, is this a first order process, that's what we would look for, right? Is the half-life a constant value? All right. Thank you for listening. Be good, and I will see you soon. Bye.